Hi there. Let's talk about AC and in particular the mysterious RMS or root mean square value, because I noticed some strange behavior with my True RMS multimeters that had me confused for a bit. You see, it all started when I noticed that the RMS voltage produced by my AC converter, which will be one of my next videos, was rather sensitive to the duty cycle of the square wave, but it shouldn't be, because the theory says that the RMS of this waveform doesn't depend on duty cycle. The blue meter is showing the AC RMS voltage and the red one the duty cycle. You can see that the voltage drops as the duty cycle changes. It turns out my AC converter had nothing to do with this, it's rather a feature of the multimeters. Here is such a square wave from my function generator with 5 volts peak to peak and 50% duty cycle, and the RMS value calculated by the scope is 2.5 volts. If you observe the RMS value while I change the duty cycle first to 60% and then to 70% and then to 80%, you see that it doesn't change much despite the fact that the waveform looks now very different. This is in line with the math for RMS for this waveform. Now I do the same test with two multimeters connected, both display AC volts through RMS. The small one on the right is instead showing the duty factor. At 50% the RMS values agree with each other and the scope value of about 2.5 volts. There's some noise on the signal due to the long cables, which cause a slightly higher value, but for this test it doesn't matter. At 60% the voltage has dropped already. At 70% both are reading about 2.33 volts. And at 80% we are down to 2.03 volts. Repeating the same test with my two bench multimeters, the duty cycle is again displayed by the small red multimeter. You see that the RMS values agree with each other and the values shown by the handheld multimeters. I would have understood if one multimeter got it wrong, but they all do exactly the same. The odd one out seems to be the scope. But in fact, the scope is the only one that showed the correct value of about 2.5 volts RMS. Here's why 2.5 volts is correct and independent of the duty cycle. In a 50% duty cycle square wave, the voltage is plus V peak for half the time and minus V peak for the rest. If this voltage was driving a load, we have a positive current here and a negative current here. Power is the product of voltage and current, so effectively the area under the curve. But because negative voltage times negative current is positive power, we end up with a value that is the same as if we had a constant plus V peak all the time. Since the RMS value of an AC voltage is defined as being the value of the DC voltage that produces the same power, in this case the RMS value is V peak. In our case, V peak was 2.5 volts, so it should be theoretically the RMS value. There's also the so-called Crest factor, which is V peak over RMS, and therefore 1 in this case. I'll cover the importance of the Crest factor later. The key observation is that regardless of duty cycle, the result of the operation always ends in the same RMS value, which is V peak or 2.5 volts. So the scope was right. The RMS value should not have changed when I changed the duty cycle. Are all the other multimeters wrong? But then they all agreed with each other, which points to something else at play here. I decided to test a collection of my multimeters against a couple of other waveforms to see if there was a pattern. Let's start easy with a simple sine wave. V peak is 2.5 volts. The RMS value is 1.8 volts and the average voltage is of course effectively zero because positive and negative half waves cancel each other. All except one of these multimeters agree with the scope and show the same 1.8 volts RMS. The three that agree are all true RMS. The yellow one, which is a cheap Chinese model, uses what is called an averaging circuit instead. In this instance, it should actually show the same value as the others, but its lowest AC range is 200 volts AC, so naturally it struggles with showing such low voltages as 1.8 volts correctly, but at least it shows 1.5 volts. Both of my bench meters are of course True RMS and also agree on the 1.8 volts RMS value. To try something more fancy, here's a nice triangular wave with V peak of about 2.5 volts and the scope claims an RMS of 1.47 volts. All three True RMS meters agree with the scope and show the same 1.47 volts RMS. The yellow one gets only up to 1.1 volts. Both of my bench meters also agree on the 1.47 volts RMS. Here's something a bit more exotic. This is the output of a sine wave after a full bridge rectifier. Basically all the negative half waves are flipped upwards to the positive side, which also doubles the frequency. Note that my function generator was set to 5 volt amplitude, so in the previous cases where all the waves were symmetrically around 0 we had a V peak of 2.5 volts, but now V peak is 5 volts and we have a positive average of 3.19 volts and an RMS value of 3.54 volts. And that is interesting. All True RMS multimeters agree on 1.52 volts while the yellow one shows a whopping 6.3 volts AC. You can also see that the frequency is now 100 Hz. Let's check what DC values we have. All 4 meters agree on 3.18 volts, which matches the average shown on the scope. The BM869 can show AC plus DC, and that value of 3.53 volts actually matches the RMS value shown on the scope. Both of my bench meters also show the same strange RMS value as the handheld meters, 1.52 volts. They also agree on the 3.18 volts DC. For good measure, I include a sine wave after a single diode rectifier. Basically, the negative halfway is simply cut off. V peak is 5 volts and we have a positive average of 1.61 volts and an RMS value of 2.5 volts. As with the full bridge rectifier case before, all 3 True RMS multimeters agree on an RMS voltage of about 1.91 volts, which is quite different from the scope value of 2.5 volts, while the yellow multimeter shows 3.2 volts. On the DC side, all meters agree with the average value of around 1.6 volts shown on the scope. Again, the BM869's AC plus DC display of 2.49 volts matches the RMS value shown by the scope. And the bench meters repeat what the handheld meters were showing, 1.9 volts RMS and a DC value of 1.6 volts. Homing in on DC pulses, here's one with 50% duty cycle going from 0 to 5 volts. Its average is of course 2.5 volts as you would expect, and the scope declares its RMS value to be 3.51 volts. All True RMS meters show the RMS as about 2.48 volts, while the yellow multimeter shows 5.1 volts. As for DC, all 4 handheld multimeters agree on 2.5 volts, which matches the scope's average voltage. As before, the AC plus DC value of 3.52 volts agrees with the RMS value on the scope. And the bench meters follow exactly the handheld meters by showing 2.48 volts RMS and also agree on the DC value of 2.5 volts. Changing the duty cycle to 90% and both the average has increased to 4.47 volts and the RMS value is now 4.71 volts. The RMS changes because this is a pulse, not a plus-minus square wave. All 3 True RMS meters read about 1.48 volts, while the yellow one reads a massive 9.2 volts. But all 4 meters agree on a DC value of 4.49 volts, which matches the scope's average readout. The AC plus DC value of 4.73 volts again agrees with the scope's RMS value. There's no surprise that the bench meters show the same RMS value of about 1.48 volts as the True RMS handheld meters, and also agree on the DC value of 4.49 volts. Last not least, let's get the rectangular wave from the beginning again. Its peak-to-peak value is 5 volts, so the positive peak is about 2.5 volts. The scope measures its average as about 2.05 volts and the RMS as 2.55 volts. We know it should really be 2.5 volts, but there's a bit of noise on the line as evident on the scope trace. All three True RMS meters read about 1.52 volts, while the yellow one reads 4.4. But all four meters agree on a DC value of 2.03, which matches the scope, and the AC plus DC value of 2.54 again agrees with the scope RMS value. As before, the bench meters show the same RMS of about 1.52 volts and also agree on the DC value of 2.03 volts. You may have wondered why I picked those waveforms we just saw. The reason is they all have equations that allow me to calculate the theoretical values so we can easily determine what's wrong and what's right. The equations to calculate the RMS value and the Crest factor for sine and triangle waveforms are shown here, and considering the limitations of my setup, theoretical values and actual measurements are in agreement. The only problem is the yellow averaging meter, but as I explained, it only has a 200 volts range, so that is to be expected. I only included it because it's not true RMS, and as we have seen, some of the readouts are quite different. More interesting are the full and half rectified sine waves. For DC, or the averaging value, the measurements agree well with the theoretical value, and the scope RMS value also matches the calculated value quite well. But all my True RMS meters show a substantial too low value. A clue to that behavior is the BM869 AC plus DC readout, which shows the same value as the RMS. What really happens here is that these two waveforms introduce a substantial DC offsets, shown here as the red line. But when you switch your meter to measure AC, it is normally using a capacitor in the input to keep any DC parts out. In effect, the whole trace is shifted downwards and the red DC line becomes the new zero line. We can see the effect in action if we simply switch the scope input to be AC coupled as well. The trace moves as predicted downwards, with the average being close to zero, and the RMS value is now about the same value as the True RMS multimeters showed earlier. So the seemingly wrong True RMS values have an explanation. What the multimeters show is the AC part of the True RMS. By simply adding the DC offset, you will get the truer RMS value, which then matches the RMS equations you find in literature. However, the addition has to be done geometrically and not just by adding the DC and AC values. The DC offset is also what causes the averaging meter to show these crazy values, but I'm not sure what mechanism produces this exact value. Moving on to the DC pulses with 50% and 90% duty cycle, the equations for RMS, average and crest factor are slightly more complex. The key parameter is the duty cycle, which determines both the RMS and the average DC value. If we look at the values, we see the same pattern. The DC values are in agreement across the board. The AC coupled multimeters show a different RMS value to the scope, but the AC plus DC values match the scope and the theoretical value. In other words, we have again the problem that the DC offset needs to be added to get the correct value. And the waveform that started it all? It is clear from the equations that, as explained, the RMS value is constant, but the averaging value is not. So deviating from a 50% duty cycle, we introduce a DC offset, and as the RMS, as the geometrical sum of AC and DC components remains constant, this means the AC component must reduce in value to compensate for the increasing DC. Since my True RMS meters only show the AC components, it appears as if the RMS value is dropping when the duty cycle changes. The proof of the pudding is running the same test again, but this time the multimeter on the left is showing AC plus DC in the main display. The small multimeter on the right is again showing the duty cycle. At 50% duty cycle we have no DC component and everything is showing the same AC value within tolerances. At 60% duty cycle we see the expected drop of the AC, but the AC plus DC value stays the same. The same at 70%, 80%, and 90%. The AC value has dropped by more than a volt, but the combined AC-DC value is still the same. But my BM869 that can read AC plus DC is a fairly recent addition to my lab, and not all will have a meter like that. So what is one to do with a True RMS multimeter that doesn't have an AC plus DC option? You read the AC value 1.51 and then switch to DC. If there's a substantial DC voltage, as in this case 2.035 volts, there's no choice other than whip out your calculator and use the formula to add AC and DC manually. So square root of the sum of AC squared, AC is 1.51 plus DC squared, that is 2.035, and we get 2.534, which is the real RMS value we wanted. Sometimes, however, this isn't as straightforward as you would hope. Here I am measuring a pulse with 10% duty cycle. Both bench meters show about the same AC value. Let's check the DC voltage. Both are very different from each other. Moreover, all four handheld meters in the same situation show yet another DC voltage which is slightly above 0.5 volts. But if I switch to manual ranging and select the next higher range, both bench meters now display the correct DC value. In this case, the relative high AC voltage messed up the auto ranging for the comparatively small DC value. The problem of auto ranging, if DC and AC values are sufficiently different, is a problem for handheld meters too. Here are the meters showing the DC parts of 219 millivolts of a pulse with 4% duty cycle. That is such a low voltage that you might be tempted to switch to millivolts instead, but watch what happens. The BM869 briefly shows overflow and then happily displays nonsense for both DC and AC values. The BM235 also simply shows a wrong millivolt value. In this case, I much prefer the response of the $10 AN8008, which just shows overload. Another pitfall to watch out for is the crest factor. I mentioned the crest factor before when I explained the different waveforms I used for testing. In that little table here is a quick summary ordered by increasing crest factor values. The crest factor is important because it messes up the way most True RMS circuitry works. There are exceptions. Some very expensive bench multimeters sample the waveform into memory and determine the RMS graphically just like a digital storage oscilloscope. But if you have a reputable multimeter with True RMS that isn't of the sampling kind, it will have a crest factor statement or table in its specification. It could be an additional error percentage, like in the case of my bench meters, or a crest factor range expected by the meter to stay within its rated accuracy. In either case, if your signal is outside, all bets on what it displays are off. Sometimes you see crest factors written as ratios like 2.1 to 1 or 4.2 to 1. That's just a posh way of saying 2.1 or 4.2. The fact that the AN8008 spec doesn't mention the crest factor in a posh form or in any other way makes it questionable for use with non-sinusoidal waveforms, and frankly, for pure sine wave, you don't need True RMS anyway. The last thing I want to mention in this long video is frequency. So far all measurements were at 50 Hz, but what happens if the frequency is higher? To check, I enable the frequency counter on the scope in the upper right corner and change the frequency in stages up to 1 MHz, adjusting the time base accordingly to maintain a decent waveform display. I selected a sine wave because all meters should have no problem with the RMS value for a sine wave, and I increased the amplitude to ±10 volts to give the averaging meter a better chance to keep up. You can see that the scope had no problem in determining RMS in this large frequency range. Repeating the same sweep for the handheld meters. The frequency is set to 50 Hz, as you can see in the upper display on the left meter. You can see that all meters are displaying the RMS value except for the averaging one, which is still 300 mV short, but that's probably a limit of its 200 volt range. 100 Hz is fine for all meters. At 1 kHz, the blue BM235 is starting to show a lower voltage. At 2 kHz, it drops further, and the AN8008 is starting to drop as well. Rising the frequency further reduces the voltage more and more, and at 10 kHz, both meters are showing 0. The averaging meter has dropped slightly, but it's still going strong at 3 volts. Sometimes the simpler circuit of an averaging meter has its advantages over True RMS magic. At 50 kHz it has dropped to 2.3 volts, and at 100 kHz to just 1.7. At 200 kHz the BM369 is starting to drop, and at 300 kHz the frequency display stops, but even at 500 kHz the display was still showing 3.13 volts. Anyway, time to wrap things up. Okay, so here's the key lesson that I have learned from all this. It may be surprising to you, it certainly was for me. Just because your meter says True RMS doesn't mean you can probe whatever waveform and it will always show you the True RMS. The underlying reason is that most affordable multimeters are AC coupled when measuring AC, so they only show the AC part of the RMS. Although it's quite obvious when you think about it, a waveform may contain significant DC content, but we tend to think of wave equals AC, so that DC part needs to be added to the AC part using the formula shown earlier. And then there are the gotchas that are out there just waiting for you to get a completely wrong result. The most prominent is that in DC mode, lots of AC gets into your multimeter too, and happily confuses the auto ranging, giving half a chance. And while those meters with AC plus DC mode are generally brilliant, they open the door for DC to do the same to your AC measurements. Lastly, there's the crest factor out there to get you by degrading accuracy, and of course the bandwidth limit of your meter, reducing or even completely zeroing the readings at higher frequencies. Lots of things to keep in mind when doing such a simple thing as measuring AC. Thanks for watching.